Now let's take a look at the iterative solution approach. Here we will be talking about the Newton-Raphson family of methods. This is not the only way, but this is the most popular methods in nonlinear analysis. So what we are trying to do is, we have a nonlinear equation, and again let's take the shallow truss equation as an example case. So we are trying to solve the following nonlinear equation. P is equal to EA over L cubed Z square W plus 3 over 2 Z W square plus 1 over 2 W cubed plus the spring stiffness multiplied with the vertical displacement. And as you can see, the dependent variable is W, and it's nonlinear. We have a cubic polynomial here, and we want to solve that equation by using an iterative approach. So in order to do that, let's define a function f such that f will be a function of the vertical displacement is equal to EA over L cubed Z square W plus 3 over 2 Z W squared plus 1 over 2 W cubed plus KS W minus P. And for an exact value of W, we know that this equation should be equal to 0. Now, if we take the Taylor series expansion of this equation, let's call this equation star. We have the following: F0 plus dF0 over dW plus 1 over 2 d square F0 dW square W squared, and so on. So if we ignore the higher order terms, we end up with the following equation: Fn is equal to F0 plus dF0 dW del W. In this equation, F0 represents F computed at point O. So let's see what that means and how we can use that, okay? Now, for a given estimate, for W0. So again, let's use a figure for that. Let's say that I have the following load deformation curve. That's load P. And I have the displacement W here. And let's say that that's the nonlinear curve that we want to trace. And here, that's where we are. We have an initial W0, and this W0 is on the curve. Okay. So for a given initial estimate for W0, okay, a better approximation is obtained by setting f of n equal to 0. Now in that case, remember, this was our equation, so we are setting this f of n as equal to 0. Then W0 will be equal to minus d of f0 times dw, meaning that that's the slope of the curve at W0 location multiplied with f0. I should have the inverse here. Okay, so the slope is, we are at this point, we are using this slope So we call this slope as the tangent stiffness, and that's equal to df0 over dw. Now this load, this distance will be equal to f0, that's minus f0, and this distance is calculated as w0. In other words, I'm calculating this slope at w0 with the unbalanced load f0, and that will give me another displacement del w0. Okay, and then in that case, thus a new estimate, new and the better estimate for w is, we have w1, that's equal to w0 plus we move by an additional del w amount. So now we are at this point. This is W1, and this distance, this is the unbalanced force we have, is minus F1. Okay? And then the iterative process continues . So new displacement estimate is equal to, now we will be using the slope at this point. Now I have this slope now, and it's equal to, again we have the tangent stiffness, then we will be using minus df1 over dw. And the displacement that we calculate will be this displacement, this is del w1, and del w1 will be equal to df1 over dw inverse multiplied with f1. And please note that for values of w that doesn't satisfy equilibrium condition, function Fw gives the residual force. So when we put the W that we calculated into the main function, we get this residual force. Now, by using that residual force and the slope at the current state, we will be calculating the better approximation for the W. Now, this iteration continues like that. You add your new del W to the total displacement, calculate the residual force, and go on. Okay. Now, this method is called the Newton-Raphson method. So we say that Newton-Raphson method converges to the solution point quadratically. So it has a fast conversion rate. But the downside of this method is at every step I have to calculate the tangent stiffness matrix, and also at each iteration I have to calculate the inverse of it. The computational cost on the other hand is expensive because tangent stiffness matrix must be computed and factorized at each iteration. So for large systems, and you have to calculate the tangent stiffness. Sometimes calculating the tangent stiffness again, depending on the nonlinearity you have, may take significant amount of time. The other deficiency of this method is at limit points. The tangent stiffness is singular. So you may not obtain any solution at the limit points. Now, as an alternative, one approach is to use the initial stiffness matrix factorize it once and use it during the iterations. So here we are using the initial stiffness, we are just factorizing it just once and using the iterations. Of course, this approach will increase the number of iterations, but at the same time it saves us from calculating and assembling the tangent stiffness matrix at every iteration, and also we don't have to factorize it. So this procedure, or this approach, let's call it approach, is called modified Newton-Raphson method. So in this method, this is what we are doing. We have the same load deformation curve, and let's say that we are at again at W0. Now there's a load that I want to calculate, and I want to reach to this solution point. So in order to do that, I will repeat the iterations by just using the same slope. Come back here, same slope. So I'm not changing the slope. I'm going with always with the initial slope. So whatever k I have at this point, I'm using that slope to do the equilibrium iterations. Yes, as I mentioned, this will increase the number of iterations, but computationally it is more efficient, and this approach is called the modified Newton-Raphson method. Now, using the iterative methods by itself gives us just a single point that gives us the equilibrium point. But sometimes we might want to calculate the full load deflection curve, and for this purpose we use combined incremental and iterative approach. Because while tracing the load deformation curve, we will check if we see any limit point, if while converging to the equilibrium state, will the structure becomes unstable or not. So we want to see that. That's why in a geometric nonlinear analysis, we usually prefer to perform a combined incremental and iterative solution. So the approach is as follows. So we say that the iterative techniques can only provide a single point solution. So we get only a single iteration equilibrium point. Incremental approach can be used as a predictor to provide solution points for iterative techniques to trace the complete load deflection response. So let's take a look at what we meant here. Again, this is the load. That axis is the displacement. Again, I want to trace that load deformation curve. So what I do is I give an incremental load, a delta P, and then I will do iterations and converge to my first solution point, and then I give another load increment, delta P. By using again an iterative technique, I do my iterations, converge to the second equilibrium point. So by going this way, I will use the first incremental solution, which will be this one, as my predictor. So these displacements will be the predictors, and then by using the iterations, I'm just converting the reaching to the equilibrium. So if I reduce the number of increments in my solution, I'll obtain more solution points, and with the help of that I can trace the full load deformation curve. Now sometimes when your solution is very sensitive, so if you are very close to the limit points, if you are at the unstable region, you may want to use smaller increments so that you will go slowly, converge to the approach to the limit point slowly, and you may pass and catch to the next equilibrium point. So that's mainly the approach. We use a combined incremental and iterative solution. Now the iterations, you may use different algorithms, Newton-Raphson, modified Newton-Raphson. There are also other solution methods for that. Now in the Newton-Raphson, remember that we are using the slope at the current point again, and we keep updating the slope. In the modified Newton-Raphson, we are using the initial slope and we do the iterations. Now here actually you don't have to calculate k or the slope correctly. Any slope will help you to converge to the equilibrium point, provided that you calculate the residual force accurately. Now there are some methods as well. Instead of using kt or k, they modify the k in such a way that they get a different slope and use a different slope, converge faster, but not factorize the stiffness matrix at every step. So there are many alternatives to that, but the main family of Newton-Raphson methods, we have the Newton-Raphsons that calculates the tangent stiffness at every iteration, and a modified Newton-Raphson that use the single slope at every iteration. Now we will take a look at the implementation of these methods. Now let's take a look at the implementation of these nonlinear solution algorithms. I'll start from the Newton-Raphson method. Again, we are solving the same shallow truss example. Let's remember that. So we have a truss system. We have a roller here. We put a spring here to stabilize the system, Ks. So this distance is Z, and the length of the truss is equal to L, and we are applying a force in the vertical direction. And Z is equal to 25, the length is 2500, so this is a small deformation case. Ks is equal to 135, which eliminates the snap-through behavior of this truss. And we will be first analyzing this system by using the Newton-Raphson method. Of course, we are using an incremental iterative solution approach to trace the full load deformation curve of this shallow truss example. Now, as a starting point, this part represents the increments, and this part represents the equilibrium iterations. So what I do here is, at every increment, I'm calculating the tangent stiffness matrix. We already derived the equation for it. So tangent stiffness matrix, so I'm applying a load increment that's equal to delta P, and dividing it by kt gives me the incremental displacement, and I'm calculating the total displacement by adding the incremental initial displacements of the previous increment plus the incremental displacement, and this gives me the total force. Now this is the predictor case for me. I have a W and I will check if this delta W satisfies the equilibrium condition or not. So here the iterations start. Now the first thing that I have to do is to use this delta W and use the total displacement and see if this equation gives me the equilibrium. So if F is smaller than a certain amount, I say that the equilibrium is satisfied, and then the iterations can end. Okay, so I calculate the F and multiply PA from it. So this will be my residual force. It should be, I'm expecting it to be equal to 0 when the iterations converge. Now if it is not equal to 0, I'm calculating the tangent stiffness. So remember that we are at this point, I'm calculating the slope, I'm calculating this tangent stiffness, I'm giving the residual force. So here we are giving the residual force F, and we are getting a better approximation. So calculate the tangent stiffness, inverted, multiplied with F, you get a better approximation, and then our total displacement will be small delta W plus the whatever the displacement that I have. So this iterations continues until F is small enough. Now let's take a look at the results. So with this way, I use only 15 increments. So I get 15 equilibrium points on this full load deformation curve. And at every step, I'm converging to the equilibrium point, and I find a point on this load deformation curve. Now let's take a look at the number of iterations. So at every step I reach a convergence in almost 4 iterations. So when the nonlinearity increases at this region, I see 5 iterations. So that's a very nice number of iterations, 4 or 5 iterations, and I was able to converge to the equilibrium. Now let's take a look at the modified Newton-Raphson approach. Now in this approach, I'm not calculating the tangent stiffness. Here I calculate the tangent stiffness at the beginning of the solution. This is actually the elastic first order stiffness. Okay, so as you see, I'm not calculating the tangent stiffness anywhere in this algorithm. So we have the increments here, and I have the iterations here. So basically, again, the same approach, calculate the first predictor, go to the iterations, get your residual force, and get a better approximation of displacement by having that W added. Okay, now as an alternative, what you can do is you can decide to calculate KT at every increment, but during the iterations you may want to use the KT whatever you have for this given increment. That's also a possibility, but I just calculated once here. Now again, let's take a look at the results. So again, with the modified Newton-Raphson, I was able to trace the full load deformation curve at every increment. I reached to the equilibrium. But let's take a look at the number of iterations. So at the initial, remember that I'm using this initial slope. Even if I'm here, I'm using that initial slope. So that's why when we have a nonlinearity or significant slope change between these 2 points, the number of iterations significantly increased. And here maybe we reach to the equilibrium at 10 to 20 iterations, but when we come to this point, as you see, we have a significant increase in the number of iterations. Of course, you can avoid that if you want, if you calculate the KT at every increment. That's also a possibility. We also talked about, these are the 2 main nonlinear solution algorithm. You either update the slope at every iteration or keep the slope constant. Now there's also methods we call the quasi-Newton methods. This is something in between. I haven't talked about this, we haven't formulated that, but it's a popular method called Pfgs method. So here we neither calculate the tangent stiffness at every step nor keep the slope constant. Instead, you can take a look at the formulation of it. We are transforming the tangent stiffness at every iteration. So I'm calculating the tangent stiffness once at the increment, get the inverse of it just once, and update the inverse at every increment. And this update, we have a transformation matrix here, depends on the force and the residual force. So by using this updates, let's take a look at how it works. Again, I didn't use the exact tangent stiffness, I didn't use the initial stiffness, I keep updating it, updating the inverse of that matrix. Physically it doesn't mean anything, but mathematically it gives me a slope between the Newton-Raphson and the modified Newton-Raphson method. So with this approach I was able to again trace the full load deformation path. Now let's take a look at the number of iterations. Now with the Newton-Raphson method we were in 2 to 4, our number of iterations, and here the number of iterations are a little bit larger than the Newton-Raphson, but computationally it can be argued that it's more effective because instead of doing matrix inversion at every step, you do it once and then you keep transforming it by using the displacement increments, the displacement that you calculate at every iteration and the residual force. So what we learned here is in the iterative solution, the most important thing if you converge to the equilibrium is the calculation of the residual force. This has to be exact, okay? You cannot make any mistake here. But the tangent stiffness doesn't have to be the exact tangent stiffness. You can use the initial, you can use any slope you want. The only downside of it, if you use a bad slope, you have to perform a lot of iterations. If the slope that you are using is close to the tangent stiffness slope, then you perform less iteration. But if the calculation of the residual force is correct, at the end of the day, you will get convergence. You will find an equilibrium point.